I hope you guys are enjoying our webinar series on advanced numerical modeling techniques for tunnel analysis. And welcome back. This is Harsha Tharavati. I'm geotechnical team lead at Midas ID. So I hope you guys are all having a good weekend as well. So let's get completed in less than an hour, and then we have a good outcome out of this. So let's get started. Tunnel intersection, effect of cross passages on the main tunnel. So these are the contents for today's presentation, wherein I will just give a brief idea about cross passages. I will introduce it based, and then we'll talk about the different construction methods. It's the same as the tunnel construction method, but we'll see what are the most applicable methods for the cross passages. Then we'll talk about the importance. When I say importance, like importance in terms of designing or importance in terms of modeling. So we will talk about that here. Then we will directly jump into the software wherein I will start creating the model for cross passage along with the main tunnel. And I already had the model that is analyzed with me. We will see what is the result and how the cross passage is actually affecting the main tunnel and so on. So we will deal with that. And at the end of the webinar, we have an exclusive offer for Midas GTSNX. I hope you all already have gone through it, but I will give an idea about it again. Then that's the end. So yeah, let's start with the first thing, which is cross passages. Introduction. So basically, cross passage is a short tunnel that is connecting two main tunnels. So the main tunnels could be like constructed using an tunnel boring machine or maybe an NATM method, whatever it might be. So a short tunnel that is connecting the main tunnels is nothing but called a cross passage. And this cross passage is generally constructed every 240 to 250 meter as per NFPA guidelines. NFPA is the National Fire Protection Association. It's an US government agency, but the same guidelines followed by NFPA is taken by ITEA guidelines as well. And the major reason for the construction of the cross passage is for the emergency or safety situations, like a fire situation or an unforeseen circumstances, like let's say this is a rail tunnel and the train gets stopped. So in order to evacuate the passengers from one tunnel to another tunnel, we use this cross passages. So it's an emergency and safety related cross passage, which we are going to deal with in today's session. And then the major aspect or an important objective as in terms of designer or geotechnical designer or tunnel designer is to understand what this excavation of the cross passage is going to have an effect on the main tunnel which is already constructed. So we have the excavation of the main tunnel done, and then the lining has been kept. And later on, in order to excavate the cross passage, we need to remove the main tunnel lining. So since we are removing the main tunnel lining, so a kind of deconfinement happening over there, and there will be huge stress redistribution in the tunnel lining. So we will see whether that is okay or not, and if we wanted to go ahead, what kind of collapse or whether there might be huge increase in the hook forces of the tunnel lining or not. So we'll see all such related scenarios in today's session. So whether effect of this cross passage is significant or not. That's what the idea is with this kind of detailed analysis that we are going to do in this session. And coming to the construction methods, there are lots of construction methods, okay? The main important or the major methods that are applicable for the cross passages are, first thing is cut and cover. Let's say you're dealing with the tunnel which is of a shallow overburden, and then basically the cover, the lower cover depth. In that case, you can simply excavate the entire soil, dig the entire soil, create the cross passage, and then just backfill it. That's the idea. And here there are some advantages. It's actually wide. It have a good adaptability and is suitable for all kinds of soils. It is lower in cost and faster construction. But important thing is it should have lower cover depth, and also the ground over there, the ground surface over there is free. That means there shouldn't be no buildings, there shouldn't be enough space for the construction materials to go for and then excavation material to go out. So all that thing should be there. Only then it is feasible to go for cut and cover method. And there are many other things that influence this decision, like traffic conditions or the important buildings that are present over there, and all such related scenarios. And here, as a designer, the important aspect is the main tunnel will have almost minimal to none effect or influence because of the cross passage construction, because you're actually removing the overburden and then placing the main tunnel as well as the cross passage by using cut and cover method, right? So there will be almost some minimal or no effect of this cross passage removal on the main tunnel in this particular method. But when we go for the deeper excavations, let's say we need to use some methods like NATM, SCL, or SEM. So these are all of same methods. The principles of these three methods are one and the same. NATM stands for Neo-Austrian tunneling method. SCL stands for shotcrete, sprayed concrete lining. Yeah, sprayed concrete lining. SEM stands for sequential excavation method. The principles of these methods are same. So some people call it, they're all the same with different names. So we don't go into that. Yeah, but the idea is it's well suited for large depth or when the overburden is very high, and we have a very less space in the ground surface. So also when you have very less space in the main tunnel, wherein you cannot go ahead with the tunnel boring machine or any other methods, in that case, this NATM method is much suitable. Also, this is best suited when you're dealing with squeezing condition like a Himalayan region or maybe Alps region in Europe, wherein you have lots of huge in situ stresses, wherein you have the overburden of like, let's say 1 kilometer or 2 kilometer, and the rock is experiencing huge in situ stress or squeezing condition. In that case, yeah, this method will be very much helpful. And as a primary lining, we will use the steel ribs or the shotcrete lining on the rock bolts here for the excavation of the cross passages, and then later on segments. And then here, let's say if you are dealing with a huge stress concentrated zone, then you might be experiencing this tunnel phase to collapse. In that case, it's okay to go for the ground improvement techniques like jet grouting or phase stabilization, which can also be employed using these techniques. So yeah, this is completely flexible, and you can also include relaxation as well. So if you are again dealing with high in situ stresses and you want to reduce the cover or reduce the thickness of the lining, then yeah, we will let the rock relax first and then followed by lining later. So you have that flexibility in this kind of approach. So here you go. So we are removing the main tunnel lining in the video that you are seeing. And then we are actually confining that area wherein providing steel frames and then providing the concrete to fill the gap. And then excavating, the full phase excavation happening, followed by steel ribs. And then let's say rock bolts is also placed. And then we have the shotcrete lining. So that's how the full phase excavation is proceeding from one main tunnel to the other main tunnel. So this is the idea of the NATM or SCL or SEM method. So all the three are one and the same. This is the best suitable method, when you're dealing with high overburden or in the rocks where the stress is, the in situ stresses or the rock in situ stresses is very high. And there are many other methods depending on kinds of supports. Some people deal with wooden supports over there, with timber supports. So we have timber method or let's say instead of going ahead with the cut and okay, in the case of cut and cover itself, you can use the box jacking kind of method. So yeah, there are many different methods. Based on the type of supports, and you can choose which will be the feasible one according to your discretion in your project. So that's about the construction methods for the cross passages. We will be dealing with the NATM method in this particular approach. We will also relax the ground in the cross passage while modeling. So in the later part of the webinar, I will be using the NATM as well as relaxation in this webinar. Then coming to the importance, so what is the importance of this particular structure? I mean, this particular like a 3D modeling or this particular supports. So the idea is whenever the excavation is happening or the cross passage, especially the cross passage excavation is happening, you're removing the main tunnel lining or main tunnel lining segments that will help in generating more stresses in the lining in that particular joint, and that may be affecting the main tunnel lining a lot. So that's the reason 3D modeling is the only approach for the tunnel intersection. We cannot model the impact, or we cannot assess the impact of the main tunnel, impact of cross passages excavation on the main tunnel using the 2D approach or any other approach. The better approach is the 3D modeling. So here in this video, you can see initially we have like around 46,000 kilonewtons of the hook force in the main tunnel over there, and the excavation of the cross passage is not done yet. But when I go ahead with the excavation, you can see the excavation has been done and the lining has been removed, and some part of like let's say 1 meter of excavation is done, and we have twice the hook force already. So this entire area is experiencing twice the hook force, which is now 80,000 kilonewton per meter. So here, this kind of huge forces will be present when you're dealing with the cross passages, and we need to make sure whether this huge stresses or rather hook forces in the lining is okay or not by doing the support capacity plots, or so where you have already seen MN curve and QN curve interaction diagrams. So we need to see whether this is okay or not, and then we'll go ahead with the we will go ahead with the design. So that's how this is the importance. So this kind of 3D modeling should be there to understand whether your the TBM lining or the main tunnel lining is safe or not when the cross passage is getting excavated. So that's the idea of the cross passage in a brief way. Now we will proceed on to the GTSNX modeling, wherein we will model the cross passage along with the main tunnel, and we'll also provide some relaxation. So let's proceed with that. This is a model outline wherein I will model like around 200 meters of model in depth and 200 meters in wide. 200 meters in depth and 200 meters in wide. And here, these are the two tunnels. And here you can see the main tunnels are basically like created using TBM. So that's the idea. We are not exactly modeling the TBM forces in this today's approach, but we are going to excavate the entire diameter in one go, and then we'll provide some relaxation. Let's say we are dealing with like a huge overburden, and yeah, I forgot to say. So this main tunnel is having overburden here of 100 meters, but in the top we have like another 900 meters. A total of 1 kilometer like overburden is present in this model. So we will model the 900 meter overburden via and pressure load at the top, and then the rest 100 meter is actually modeled. And then because of this huge in situ stresses, there might be a possibility of a huge the thickness in the lining of the main tunnel will be there. So hence what we will do is we will relax the main tunnels and then followed by some the final lining over there. So once the right tunnel is excavated, the left tunnel will be done, and the diameter of 9 meters of a cross passage will be excavated from the right tunnel to the left tunnel. So that's the idea of this particular modeling. And as I said, the main tunnels will be excavated via TBM, but we are not actually modeling the TBM. Like we will be considering the wished in place kind of method. And then this cross passage will be excavated via NATM. So we will be relaxing it by 80%. And then after 80% of relaxation is done, we will go for the application of the tunnel lining. So that's how it is going to proceed. And this is a construction like a sequence. At first, the right tunnel is going to get excavated, which is then followed by the left tunnel, and then the excavation of cross passage will start from the right and then proceed towards the left. So you can see one stage gap is proceeded over there, which means 80% relaxation is proceeded in that particular stage, followed by the application of the tunnel lining in the next stage. That's the idea. So let's create the model. And this is the workflow in any FEM software, like GTSNX is no exclusion from it. So you know the geometry what to model right now. So we have 200 meter by 200 meter rock, and then I forgot to say, yeah. So here in the 200 by 200 meter rock, we have a zone inside, wherein what I will do is I will keep a very less mesh size in this particular zone. This is like a 40 by like 40 meter depth zone, and it's like 90 meter in the width. So this will be having very less mesh size, and the coarser mesh size will be kept on the outer rock. Okay, so that's how we will be doing it. So now we know the dimensions of what to model and how to model. So the first step in the modeling is the geometry creation. So wherein we'll create the geometry model, either we import it or we will go for direct application of direct creation of the model in this particular using the geometry that we already know in this software. And then we create the material. So as I said, we are dealing with and a huge rock which is having a overburden of like around 1 kilometer, and then we will input all the material properties. So here in this particular case, we are going to use the molecular material only. And then we define the properties, wherein the property of finite element property will be defined here. So for tunnel lining, we'll go for a shell element. For this rock, we'll be using the solid element because it's a 3D model. And then we will mesh the entire geometry. We'll discretize the entire geometry to form a mesh. And then we'll be using the hybrid mesh here. So you'll have hexahedral elements, pyramid elements, pentahedral elements. So which will make our life little easy in terms of analysis time. And then we will apply the loads and boundary conditions, run the analysis, we'll get the results. So we'll interpret the results as well. That's the workflow. So let's start with the geometry. So yeah, let's start modeling. So directly jump into the software. Yeah, this is the already created model, so which I will show you when the analysis is which once the modeling is done, I will directly proceed into this particular model to show you the results. Okay, so let's go to the analysis creation of the model. Okay, yeah. So when you open the GTSNX, this is what you will be asked with. So we'll go for either 3D type or 2D type. So our idea is to go for 3D modeling in this particular scenario. Let's start the 3D modeling. The gravity direction is Z here, so press OK. And then the first step is to create the geometry. So let's start modeling. Go to the geometry tab here, and then click on the front face first. And by default, the size of the grid is 20 meters, which is too heavy. So we will reduce the grid size. Actually, no need, let it be. We will be directly dealing with the coordinates. So up to you, whichever way you might be interested in. The cross passages is of 9-meter diameter. The main tunnel is of 12-meter diameter. So let's start modeling the main tunnel now. So go to the circle. So click on another circle. So the location is a center, let's say. So that's the center, which is 0, 0. And then the diameter of the main tunnel is 12 meter. So let's go for the radius of 6 meter here and click apply. So here we go. Then we will be creating the model in a symmetrical way. So let's take this model from center to about 40 meters on the right side. So yeah, I wanted to show you. So the gap between the center to center gap between it's like 40 meters. So that's what the center to center distance between the two twin tunnels is. So let's transfer this tunnel to 20 meters onto the right side and create the other tunnel over here. So let's translate, select, and then select the direction of the translation, so which will be 20 meter. Let's preview it. Yeah, 20. And then we will select the same, we'll select the same direction, and then we will copy it by minus 40 meters. Yeah, so we have two outlines of the main main tunnels right now. And the length of the main tunnels which we are going to prepare is of a 90 meters. So we are going to create an tunnel length of 90 meters. And somewhere in the mid, we will have the cross passage. So let's extrude these two. Oh, sorry, we need to select the edges. So let's select the edges. And the direction of extrusion is the global y-axis. So select the y direction. And we are going to extrude by 90 meters. So let's have the 90-meter excavation done. Yeah, that is the important part. Once this is done, what we will do is we will create the diameter of the like cross passage. So let's go to the circle again. And here, go to the front view. So select the center, and then the diameter is like around 9 meters. So we'll provide a radius of 4.5 meters and press OK. So we have this. What we will do is we will translate this by 45 meters somewhere in the center, and then we will rotate this by 90 degrees so that it will be perpendicular to the main tunnels. So let's translate this along the global y direction. 45 meters. Apply. And then here we have the rotate option as well. Select or rotate. So we are going to rotate this particular object, and then we are going to use the axis of the tunnel itself. So yeah, here I will hide this too. Okay. So we've selected the center of the circle, and then we'll copy the second vector, which will be the same with the depth of like around 45 meters or 4 meters. We are just providing the vector here, so which will be vertical right now. And then we are going to rotate it by 90 degrees. So yeah, so this is what we are interested in. Now let's extrude it by some around, let's say the center to center distance is 40 meters. So let's extrude by 40, and then we will translate 20 meters onto the other side. Oh yeah, so let's extrude it in global X direction. Okay, now let's translate it to the by 20 meters onto the other side. 20 meters, which is negative in direction. Yes, the cross passage is also modeled. Now, what we will do is we will cut your cross passage from the main tunnel on the left side as well as right side. So in order to cut your cross passage from the main tunnel, we need to use the Boolean operation. So let's go to the solid Boolean operation. And then we will use this cut option. Here, the target which we are cutting is the your cross passage. It is piercing into main tunnels. So what we will do is we'll select the target object, which is the cross passage. We are going to cut it. And the tool will be main tunnels. And we are not going to delete the tools. We need to have both the tools ready, be there itself. So press OK. All right. So here we go. Now the cross passage is divided, and you can see if I hide both the main tunnels, so you have a proper cut over there. So this is what we needed, and we got what we needed. So we have main tunnel, and then we have cross passages as well. Then, like as we said, we are going to have the rock mass created, and this rock mass will be having 200 meters in depth, 200 meters in width and depth. So let's create the outline for the rock mass. So here we go. So this is okay. So the inner rock mass which we are going to create is for lesser mesh size, so that the stress transfer will be very good because the mesh size is finer, and then the accuracy will be much better. And then let's create a bigger model. So 100 onto the other side and 100 onto the other side. So which we have like 200 by 200 meter model. So this is what the outline of the rock is looking like. So when we consider from the top of the tunnel to the top of this particular point, the Z coordinate is like around 94 meters. Okay. So we have like around 906 meter still not model. So instead of modeling directly the entire 1 kilometer overburden, we will apply the additional 900 meter overburden as a pressure at the top. Okay. So we'll just ignore the 6 meter overburden. So we will model the 900 meter overburden on the top. Then let's extrude the both inner rock mass as well as outer rock mass. So the extruding direction is the global Y, wherein the length of extrusion is 90 meter. So here we go. This is what we are going to have. Oh, okay. I think I haven't selected the entire. So let's extrude both of them individually. $90 meter. Click apply, and then select the other one, which will be again 90 meter. Okay. So that's what we have now. And we need to make sure the tunnel excavation of the cross passage will be done for every 2 meters. So that's the idea. So let's divide this entire tunnel into many solids of 2 meter in width. Okay. So let's create the surface just to cut the cross passage. For that, I'm going to provide the work plane right now, which you are seeing is in XZ plane. I want to go ahead with the YZ plane. Okay, so YZ or ZY plane. So in the work plane, we go for YZ plane. So when I go to the side view, I have the work plane ready for. So this is the rectangle. I will go for the rectangle. Click on Make Face. Just create a face so that your cross passage will be inside that face, like this. And then we do not want this, we'll just hide them. So translate this particular surface by 20 meters onto the other side, onto the cross main tunnel side. So we'll select the global x-axis. We'll just move it by 20 meters. Okay, this is the initial part. Now, what we will do is we will just uh, copy this entire surface for every 2 meters onto the cross tunnel. I will hide the curves as well. Yeah. So target is selected, direction is also selected. Let's go to the copy, and then we will use 2 meter for 20 times. Preview. Yeah, there you go. So here we have, we do not need the last 3 and the first 3. As also, I do not want the 4th one as well, because I want to excavate from here to here in one go. So that's the first excavation in the cross passage. Then we have the 2 meter excavation and so on. So I'm deleting the unwanted rectangles or surfaces right now. So this is what we have. So let's go for the divide option. So we will divide or cut this entire solid into many parts, many different parts. So this is the solid divide option. Here, this is the solid divide option. So we select the target solid, and then we will select the faces. Here you can use the intersect option, wherein I can simply select all the faces in one go. Okay. And then we want to delete the tool. We want to delete the original. That means original entire the biggest panel will be now divided into the smaller ones. So the original bigger one will be deleted. We will be only having the smaller ones now. So press OK. Yes, that's what we are interested in, and that's what we got. 1, 2, 3, 4, and so on. So these are the different solids we have. So if you hide them, we have many different solids. So show all. Yeah. So this is the model that we have created till now. I'm going to hide the grid. I'm going to hide the the axis and the work plane. So this is what we have. So let's hide the curves as well. Now, we do not know if all the solids are in contact with each other or not, right? So we will just check whether the solids are in contact with the surrounding solids or not. For that, you need to go to check duplicate. Click on apply. So here we go. Only the cross-passage solids are in contact with each other, but the cross-passage solid is not in contact with the main tunnel, and the main tunnel is not in contact with the surrounding rock mass as well, right? So what we need to do is we need to use the auto connect option. So let's go to the auto connect option, select all the solids, and in one go, we will have all the solids in contact with each other. So let's check the duplicates again. So here we go. At first, the inner rock mass is in contact with the outer rock mass. That's the reason you have the orange features here. Then, here, we have the main tunnel in contact with the inner rock mass. And that's the reason you have orange face here. And here we go, the cross passage in contact with the main tunnel, and then we have the orange face. So that's how you can ensure that each solid is in contact with the surrounding solids or not. So that's what we can achieve using this auto connect in one go, right? So yeah, that's the geometric model which we wanted to create. Now we will go ahead with the material definition. So go to the mesh tab and click on material. Click on isotropic. So we are going to use the isotropic connection now. And we are going to use a Merck column. So I'm not worried about the type of material now, because the major interest in this particular model is the effect of cross passage on the main tunnel because of the 1 kilometer overburden. So we'll consider for the preliminary analysis using Merck column. That would be sufficient for the even detailed analysis as well. So let's start giving the drop details. The elastic modulus is very high. It's 285,000. It's like 28 lakhs 50,000 or 2.8 million. And the Poisson's ratio is 0.3. The unit weight is 26. Okay, So now, if you remember, I said the overburden is of like 1 kilometer, and I modeled 100 meters here, and the rest, the 900 meters at the top, is not modeled. So the 900 multiplied by unit weight will be applied on the pressure as the pressure on the top of your the rock here. So that's what we'll be doing. And then we'll give the name as rock mass. We'll go to the Chorus tab. Let's provide 26 again. And in the nonlinear, the rock is so good. So based on the elastic modulus itself, you might have an conclusion like it's just so good. It's a very good elastic modulus or very good rock over there. So hence the cohesion is like 2100 and friction angle of 27 degrees. And press apply. So the rock mass has been defined. And the second thing is we are going to define the soil. The rock has been defined. The second thing is we need to define the like a lining, which is concrete over there. We will use the elastic model, and let's name it as lining or concrete, whichever is okay for you. So we will have elastic modulus of 12 GPa. So which will be 3 more zeros. Yeah, 12 GPa, and then Poisson's ratio of 0.2, and then we'll go for the unit weight of 24. Press apply. So two materials have been defined, which is the rock mass followed by the lining. Then we'll go for the property definition. The first thing is we'll define the 3D property, which is the rock property over there. So we have the rock mass, and then we'll give the same as, oh, sorry. Oh, sorry, yeah. So select the rock mass, and we'll give the name as rock. And then the next thing is we need to define the lining. So we have two linings to define. The first thing is the lining of the main TBN tunnel. The second thing is the lining of the cross tunnel. So let's use a shell element for it. So we are going to use the shell element to define the lining. We'll go for the main tunnel lining, main T lining, okay? So the main tunnel lining is of 0.5 meter. So the thickness is 0.5 meter, right? So we are dealing with the 12 meter diameter tunnel, and then the thickness is of like around 0.5 meter. And we are using the lining material over there, and press apply. Then we have the cross tunnel lining. So we'll give the name cross tunnel lining. And the thickness of the cross passage lining is going to be 0.3 meter. So if you remember, I said we are going to relax the cross passage by 80%. So hence, since we are reducing or relaxing the rock, we are letting the volume loss to happen. Hence, the stresses will be lower. Hence, the lower thickness. So the relaxation coefficients and the related study has to be done prior to this analysis. So once the GRC curve, once the LDP profile and the support capacity plots are drawn, so which you already have gone through in the NATM session in this tunnel webinar series. So I'm just assuming the relaxation as 80% now in the cross passage and 30% in the main tunnel. So that's the assumptions that I'm going to take in this current model. Then we'll see how it goes in terms of analysis. So 0.3 is the thickness of the cross passage. Press OK. So we have three models, three properties. Let's close. So that's the idea. Now let's start meshing it. So hide both the rock masses. We will start meshing the tunnels first. So we'll go to the 3D mesher, go to generate, and click on 3D. So let's mesh the cross tunnel now. So we'll give the mesh size of around 1 meter, and then we are going to use hybrid mesher. Select the row property, and we'll give the name cross tunnel XT, and press apply. Right. So in the mesh tab, in the models work tree, you can find the mesh tab. So this is the like all the names that we have given. So XT here and so on, but these are all randomly placed, okay? So XT1 maybe here, XT2 maybe here, so we need to rename them, right? So let's go to the rename option here and select all the mesh sets. And we are going to excavate from right side to the left side. So this should be first excavation, followed by second, third, fourth, and until the last. So we'll be dealing with the global y-axis in a descending order because it's positive, but we are going to in the descending order. So what we will do is we'll give the name cross tunnel, press apply. So this is cross tunnel 1 and cross tunnel 2 here. So the names are properly placed. So if I click on sort by name, cross tunnel 2 to 3, 4, 5, 6, and so on. So the meshes of the cross passage is done. Let's create the mesh for the main tunnel. So select both and click on give the mesh size of 1, hybrid measure, rock mass, and press OK. So now what we will do is we will provide the name set first, and then we'll mesh the surrounding rock mass. So this is the AutoMesh 3D for the left tunnel. So we'll give the name left tunnel, apply. Here, this is going to be right tunnel, apply. Click on apply here. Okay, the names are not changed. So let's mesh the rocks. I mean, the rock mass surrounding here. So let's go to the 3D measure. Select the inner rock at first. So the inner rock, for the inner rock, we will provide the mesh size of 2 meters with the hybrid measure again. And we'll give the name inner rock mass. Press apply. And then we'll provide the mesh size of 5 meters on the outer rock mass. So if you see, I have been individually meshing all the solids one by one, right? So I mesh the cross passage followed by the main tunnels and then followed by the outer rocks. So this way you will have a command on providing what mesh size to be taken for different solids. But if you wanted to mesh everything in one go, you can simply use the size control to provide number of mesh sizes for the bigger solids, and then just select all solids, including cross passages, main tunnels, and the rock masses, and just press OK. The software will automatically give that particular mesh size that you had selected in one go. But I like this, wherein I have a control on what mesh size to be given to different solids. So now I will use 5 meter mesh size for the outer rock mass. Okay, this is going to be outer. Press OK. So now once the meshing of the solids is in, we need to provide the lining. So we have the lining for main tunnels, we have the lining for cross tunnels. So we will define them, and then later on we'll apply the overburden pressure of 900 meters, and then we'll define the construction sequence. So that's the idea. So let's start from the meshing of the linings after this. Yeah, 60%. So yeah, a total of like almost 200,000 elements are already created in this model. So let's hide all the geometry as well as meshes. So this is the entire mesh we have. Let's hide the meshes. And then I'm going to extract a 2D mesh out of the 3D meshes. So this entire solids have already been created with the 3D meshes, right? So using the extract option in this software, we will extract the 2D meshes out of the 3D meshes. So that's what we will be doing. So further, at first, let me start with the cross tunnel lining. So I will select the main tunnels and then hide them. So now we will go to the extract option. So hide the mesh sets as well. So we are going to extract a 2D mesh. So the shell elements is an area element or a 2D element over there. Hence, we need to select the face or surface. So select all the faces, something like this. So you have all the faces selected, all the circumferential faces, not not the tunnel face. Okay. So we will give the cross tunnel lining, and we want to register based on ownership. So if we do not click this, so entire lining will be of one single mesh set, which we do not want. We want every single object to be of a different mesh sets. That's how we can go ahead and activate one lining one by one. So press OK. So here we go. We have like around 14 mesh sets here to be lining. So I will hide all the solids. So this is what we have, the 2D lining. So now what we will do is we will rename them. So click on rename and select all the linings according to the global x-axis. So because it is aligned in the global x direction in the descending order. So we will give xt cross tunnel lining and press OK. So we'll give sort binding. So here we go, cross tunnel lining 1, 2, 3, 4, and so on. The 14th will be the last one. Then let's extract a 2D mesh out of the main tunnel linings as well. Okay. So these are the main tunnels, and I will hide all the meshes. So these are the two main tunnels. So let's extract. This is the extract option. Face. And this is the main tunnel lining. We'll give the name line, and then we'll later on change. But the important thing is this particular two things will be of different mesh sets because we are going to excavate this segment lining and then followed by the cross tunnel excavation. So we'll define them again. So go to extract and then select the face, and we'll give the main tunnel lining. We'll give the name right main tunnel lining excavation because we need to remove this later on. Similarly, select these two faces. This will be given left main tunnel lining excavation. Okay, that is all. That is all with the meshing part. So, but let's rename them. This is the left main lining, and this is the right main lining. Apply. So the modeling is almost done in terms of geometry and meshing. So let's proceed on with the loadings and construction stage definitions. So the next thing is we'll go to the static slope analysis. In the load set, we'll go to self weight, and we'll give the name SW as a self weight and press OK. Then we'll go to the pressure. So we are going to apply a pressure of 900 multiplied by 26, so which is of 23,400 kilonewtons on the top. So select all the faces on the top, and we'll go for 23,400, which will be overburden pressure. Press OK. So that's the pressure that we have applied, and yeah, that is all. So let's start defining the construction sequence. So at first, I will hide the inner rock mass and the outer rock mass so that it will be easy for you to understand these stage definitions. So we'll give the name tunnel intersection. And we are doing the stress analysis. You can do lots of analysis, but now we are dealing with stress analysis. Okay, the first stage, we are going to have in situ stage. And we are going to have all the mesh sets except the lining will be activated. So inner rock mass, outer rock mass, let's activate them. No lining, no excavation. Left tunnel, right tunnel will be activated. So we will, whatever is activated here will be shown. So let's click on activate. Now the cross tunnels will also need to be activated. Yeah, and then the overburden and self weight. I forgot to apply the boundary conditions. So let's go to the boundary here and go to the constraint. Click on auto and we'll give the name GS, ground support. So let's activate the ground support. And because of the self weight, whatever the displacement that might occur, we do not need. And because of the overburden, whatever displacement that might occur, we do not want. We are only interested in the displacement that might occur when the excavation of the cross passage is done. Click save. Then in the next stage, we are going to have an excavation of the right tunnel. So right tunnel, where is it? Where is it? Yeah, here we go. So the right tunnel is excavated. But as I said, this is a 1 kilometer excavation. So if you directly apply the lining as and when the entire tunnel is excavated, that means all the stresses will be taken by the lining itself, so which may lead to have very huge thickness in the lining. That might not be good economically. So hence we will relax this tunnel, and then we will relax it by 30% at first in this stage. And in the next stage, we will activate the lining, and then the rest 70% stress from the overburden will be taken by the lining. That means we are relaxing the rock by 30%, and the 70% will be taken by the lining in the next stage. Press OK and apply. So here we'll give the name right lining. So right lining is here. So here now the 70% of the stress will be taken by the lining. Now go to the next stage. We'll give the name left excavation, left tunnel excavation. So here we go. So we'll remove the left tunnel in the deactivation stage. And again, the same. So we will delete this one. Here we'll have 0.3 and here we have 0.7. That means 30% relaxation followed by 70% in the next stage, but that will be restricted or resisted by your lining. And press apply. So now we will give the name left lining. So this is go up. Left lining. Yes, that's how. So now, until now, everything is good. But now, from in the next stage onwards, we are dealing with almost relaxation and then lining. We are going to define 24 almost 28 stages, which will take a lot of time, and I may find some human errors while doing. So, hence, instead of going ahead with this manual input definition, I will go with the stage visit. So here we go. So now in the stage visit, what I will define is from S5 stage. Okay. In S5 stage, we are going to have excavation of the cross passage, and then that will be followed by the next stage wherein the lining will be activated, right? So we'll go for the mesh set. So where is the cross tunnel? Here we go. Cross tunnel. We are going to remove it, and the excavation will start from 5th stage. So write the number 5 here, and for every 2 stages we are going to remove it. So click on input 2 here. So that's how the cross tunnel will be removed every 2 stages. Then the cross tunnel lining will be activated from stage 6. Okay. So let's give the name 6, and then it will be activated every 2 stages and apply assignment rules. Okay, you can see cross tunnel lining. So almost how many stages? So we have 32 stages defined. Press OK, and then we'll go to this particular stage. So we have all these stages now defined. Okay. So now one more thing is, when I forgot to activate the lining of at this particular location. So I also need to activate right tunnel lining here, the excavation one. That means here, the lining over here. I have given it a different name. So what I will do is I will show you the property thickness, from which you can understand. So I activated the entire lining, but the lining on the face of the cross tunnel is not activated. So let's activate right main tunnel, which will be excavating it later on. Hence, I have given the name XEX. So the cross tunnel, the main tunnel lining has been completely filled now. Then you go to the left lining. Similarly, you activate the left lining excavation here. This is the one. So left main tunnel excavation. Yep. Then you go to the next stage, wherein the excavation is happening here. But here we are going to excavate the right main tunnel excavation as well, right? So these segments are excavated, followed by the excavation of the tunnel, and in the next stage we are going to have the lining activated. But as I said, in this stage we are deactivating the cross tunnel as well as the right main lining. But we are going to deactivate it by relaxing it. So in this stage, we are going to relax the cross tunnel by 80%, and then in the next stage, the rest 20% will be taken by the lining. So when I press OK and go to the next stage, click on Save. So now this lining, which you are seeing right now, will be taking only 20% of the load. So what we will do is this lining will take only 20% of the load. So we will do this for all the stages. We'll do the same for all the stages. So let's copy this LDF. This is 5th stage. We'll copy to every alternate stages, odd number stages. 13, 15, 17, 19, 21, 23, 25, 27, 29, 31. That's all. So that's how for every cross tunnel excavation, we have the LDF defined. Okay. So that is all. Let's run the analysis and see the results. So the main, let's define the analysis case. Construction stage, we are running the construction stage analysis. So we'll give the name tunnel intersection. Initially, we are going to run the K0 condition, and then this is important when you are dealing with this kind of analysis. So what it does is after every stage, it will calculate the new positions of the nodes because there will be deformation happening, and then on to the deformed shape, the lining or the newly activated elements will be provided. So this is important. Yeah, that is how. The modeling is done. All you need to do is you need to simply perform. But I already have the analysis with me, so let's see the results directly. So this is the model with the analyzed condition. So let's see the deformations at first. In the initial stage, we have zero displacement because we cleared all the displacement because of the overburden and the self-weight, right? Now, in the we will see the displacement in the tunnel. We are not interested in the surface sediments, but that's the reason I'm hiding the inner rock mass and the outer rock mass. So we are interested in displacement. The main tunnel has been like this is a stage bar. If you scroll down the stage bar, you will be able to see the results and check the results in that particular stage. Right now, the right tunnel has been excavated. So you can see the name, which is the right tunnel. And in the next stage, the lining will be activated. So when the right tunnel is excavated, if you activate the inner rock mass, you can see the right tunnel has been excavated, and the value is like around 23 mm. So if you remember, we relaxed it by 30% in this stage. The rest 70% will be taken by 70% of the stress will be taken by the line in the next stage. So I'm going to hide this inner rock mass. And yeah, that's how you can see this lining is now having 72%, 72 mm of total displacement. This means your lining is now taking the rest 70% of the load. Hence, you got increase in the deformation from 23 to 70 mm. If you scroll down more, you will have the right tunnel. So if I activate the inner rock mass, you can see the excavation. If I go to the probe view, I can see it's around 30 mm at the crown of main tunnel on the left side. So when you go further, it's experiencing 80 mm because of the rest 70% of the relaxation. Okay, so let's hide the inner rock mass. And now here we go. So the excavation of the cross passage is starting right now. What I will do is I will hide the left on right main tunnel. So let's see only the deformation contours of the cross passage. Okay. So when you see here, I will show you the deformation. So here we go. So you can see a kind of a small bulging over there. So the value is like around 173 mm. So the tunnel face in the cross passage is now having 173 mm in the first excavation stage, right? But this is actually of 80% relaxation, and then followed by the rest 20% when it is relaxed, the lining is resisting the 20% load. And now you can see the tunnel face is like 360 mm in deformation. So if it's very high, then that means the tunnel face is going to collapse. We need to start ahead with the face stabilization. Maybe we need to go for jet grouting, or we need to provide some shotcrete lining over there, and then we will go ahead with the benching, heading, and so on. So that's how you need to go ahead here. The face stabilization is needed in such a case if the deformation is very, very high. So now you can see, so the deformation is still higher inside. It's like 400 mm, and that is how you have. So if I activate the values, so you can see the deformation in the cross passages. So at the end of the model, the cross passage is experiencing the deformation of maximum of 173 mm at the start, and at the end it is experiencing almost 142 mm. In the middle, it's like around 100 mm. So that's the idea. Now, what we will do is we will see whether the tunnel lining is going to have the main tunnel lining is going to have any effect because of the excavation of the cross passage or not. So that's the idea. So let's activate all the main tunnels, right? And here we will go for the right tunnel lining. Here we'll activate the membrane forces. So we are interested in shell element forces. So what we need to do is every time when we are dealing with the 3D models, we need to develop our own the coordinate system to see the effect of the results for the hook forces and so on. So I already created my own coordinate systems. I simply click on add and then provide my own coordinate system here. So if you see, here we go. These are the new coordinate system. So here we have the new coordinate system for the right tunnel, left tunnel, and the cross tunnel. which is somewhere inside. Okay. So you may ask, what is the need for this? So you can always get the results in any direction that you wanted. Sometimes we wanted to see the results in the local axis. That's okay. You can get the results. If you want to see the results across the global axis, that's okay. Because these results, according to the axis of our interest, can help you out in judging the support capacity plots, or can help you out in judging the bending moment and then transferring to your structural team where they can understand easily, because they're always interested in about which axis is the moment, or is about which axis is the as the deformation is. So they're all interested in such kind of questions, so which will be very much helpful when you deal with your own coordinate system. Okay, so now let's go with the membrane forces. Here, I go to the general in the properties tab, and then you can define your own coordinate system. So here I have chosen left main tunnel, so press apply. So now the results are all like with respect to the left main tunnel. Now, what I will do is I will show you the results at this location. So the hook forces is like around 46,000 here, 46,000 and 46,000, right? Now, the excavation of only the right tunnel is done. The cross passage excavation is not yet started. So when I scroll down this, there you go. The first excavation of the cross passage is done. And you can see the jumping in the hook forces in your main tunnel is like almost 2 times. Previously, before the excavation of the cross passage, it's like around 40,000. Now it's almost 80,000. So we need to take this 80,000 kilonewton meter into account, and we need to plot our capacity demand plots and whether see whether they are safe or not. So if you scroll down more, and the cross almost another excavation is going to happen, and now it increases to 98,000. So you can see almost 100,000 is already there, the hook forces in some locations. If this hook forces or and the bending moments at those locations are so high, then that might lead to the collapse of this intersection, and all the overburden will flow to the main tunnel, and that may lead to a lot of time in the removal and the delaying the project. So it will be a disaster at that time. So hence, the tunnel intersection is of very important and needful thing to be able to understand the behavior of the main tunnel just after the excavation or during the excavation of the cross passage. So if you go ahead, you can see the lining. So we have still the cross passage excavation to be done. And at the end, you can see the values. So finally, the hook force values is like around 123,000 kilonewton per meter. So which is very, very high. And we need to plot our, what do we say? We need to plot our the support capacity plots to understand whether this force is okay or not. Otherwise, we need to redesign our entire tunnel. That means instead of just 30% relaxation on the main tunnels, we need to go for more relaxation, maybe 50% or 70% on the main tunnel, and then maybe more percent of relaxation on the cross passages as well. So which will be a nightmare when you have a lot of huge relaxation in the field. As a designer, we are just dealing with the values. But in the field, while seeing the strain gauges, when they are dealing with the huge strains, they need to be very careful, and that's how the construction works. Okay, now I wanted to see the let's say the plastic status from the first stage. When the right tunnel is excavated, in the next stage, I wanted to see the plastic states. So here we go. I relaxed this entire tunnel in this stage by about 30%, right? So 30% relaxation, you can see this tunnel is already into plastic zone. So which suggests you that this is a huge in situ stresses ground. And if I select it correctly, so the plastic radius is of 1.66 meter plus what is the diameter of the tunnel? 6 meter. So 7.66 is your plastic status or plastic radius. So during the main tunnel excavation, the first stage, when you go to the next stage, you still have 1.66 meter only. So now what we will do is we will just see how the plastic status is changing when the cross passage is getting excavated. There you go. We are starting the excavation of the cross passage, and we are relaxing this tunnel by around 80%. You can see the entire cross passage is in the red color zone, which is the plastic zone. So you can see this entire zone is in plastic zone. Even the tunnel face is entirely in plastic zone because you are experiencing like around 400 mm of displacements. So that's the idea. The blue color points are nothing but the unloading reloading failure. So which represents that moculum material does not have the unloading stiffness. So whenever there is some unloading happening, it will show you as an unloading failure because it takes the original elastic stiffness, but it doesn't take the unloading stiffness because it does not have. So if you want to consider the unloading stiffness as well, you need to go with either hardening soil or moculum material model. But this is a rock. It's not that needed to go ahead with the advanced models for like hardening and so on. Generalized hook ground or moculum will be sufficient in this huge high in situ stresses kind of analysis. Okay, that is the idea for today's presentation. Okay, thank you all. Thank you all for listening until now.